Tamara, and I will present a paper entitled Experimenting with Ensembles of Pre-trained Language Models for Classification of Custom. I will present multi-level classification results using deep ensemble models trained on legal and regulatory corpora. I will present the motivation and briefly the background of multi-level classification with ensemble deep learning, and then I'll show the methods, experiments, and results. The field of law and regulations defines legal terms of contract between financial institutions and companies or range of business activities. To avoid penalties, financial institutions and companies need to know which rules apply to their business domain, which is a difficult task considering the large number of regulations, their cross-activity span, and their specific vocabulary. Experts are required to categorize types of business activities a contract relates to, or to label types of individual clauses, which is an expensive and time-consuming task, as the law and regulatory corpora has a domain-specific language where words can be used in a new context with a new meaning. The data is multi-labeled and highly imbalanced. We can see we can have up to 18 labels per instance in the EURLEX 50K dataset. Data can also have a large word count per instance. Some documents can have over 40,000 words. As a result, automatic classification of legal and regulatory documents can reduce costs, effort, and time. Imbalanced data distribution increases the complexity of the learning problem, as stratified sampling cannot be applied to create a test train split that includes all labels. Iterative methods for test train split have been proposed to ensure similar label distribution in both test and train sets as the ones proposed by Lillis, but these can be time-consuming and sometimes don't reach convergence. Traditional methods for multi-label classification are algorithm adaptation, problem transformation, and ensemble learning. And we know that problem transformation methods can lead to ensemble methods as well, as multi-label data can produce ensembles of models using one versus all, one versus one techniques, resampling and subsampling, or rearranging the data into domains that match labels distribution or their hierarchical arrangement. Ensemble methods are commonly used on imbalanced data sets with data oversampling techniques. Using ensemble methods is advantageous as aggregating predictions from diverse models improves performance, and increasing diversity decreases generalization error, further increasing performance. Methods to generate diversity are bagging and boosting, and such meta-learner methods can be applied to any base learner, including deep learners. Using pre-trained NLP transformers as base learners is advantageous as well, due to their large context and semantic-aware language model, which can improve multi-level classification results even on small data sets. Starting with the foundation model, but a wide variety of pre-trained transformer models is available, improving the pre-training methods or the domain-specific vocabulary, as in legal BERT and its variants, or enabling input sequences larger than 512 tokens. All these improvements come with a trade-off between model performance and computational expense, as memory and processing time. To enable efficient use as base models in deep ensembles, we choose transformers with low to moderate memory and processing requirements, as BERT, Roberta, Albert, and XLNet, all as base variant. As real-life custom data sets are highly imbalanced and have a small number of instances, they require efficient data sampling methods that enable all labels to be represented in both train and test sets. For this, we have designed a fast pseudo-stratified sampling function, which randomly extracts without replacement instances that represent each label in a number proportional to the frequency of each label. And we define an integer parameter ratio in, which configures the numbers of entries to be extracted for the test set. For the training set, we keep only the instances that are not included in the test set. The random process can be repeated if not all labels are included in the training set, and the correct label distribution is achieved fast within 2 repetitions. In figure 3, we can see the distribution of labels from train and test sets, which is quite similar. And the evolution of sizes of data in the train and test sets are also shown in figure 2. Regarding the data sets, there is a scarcity of custom legal texts, which are often proprietary. Some curated collections of legal texts have been made available recently, and some are included in the LexGlue benchmark dataset, from which we have chosen to use multi-label datasets as ECHR A and B, which are case descriptions of the European Court of Human Rights, and EURLEX, which contains EU legislation and has 100 most frequent labels from label 2 of the EURLEX 50K taxonomy. The LexGlue datasets are designed for natural language understanding and include a temporal concept drift in the development test datasets, which means that data in these tests and development sets is issued at a later time, within 5 years of the documents included in the training set. To limit the concept drift, we use only the original training dataset, which we split into new, smaller train and test sets, which include data collected within the same time interval, therefore limiting the concept drift. As a result, using our subsampling function, we generate custom data sets A, B, and C from the ECHR A and B respectively, the data sets A and B. You can see they have a smaller number of instances, but still keep 10 labels. And dataset C, which is extracted from the EURLEX train regulations dataset, and from which we only keep the top most frequent 50 labels. NLP transformers, as Pat, Albert, and Roberta, can process a maximum input length of 512 tokens, which is much less than the text length in the legal datasets. To deal with large text lengths, there are several methods that are well known as text truncation. Recently, hierarchical methods have been proposed by Chalkidis, which uses hierarchical transformers that generate embeddings over the entire text and then encode these again using a sharp transformer. And data transformation methods, which we are using here, where we provide text splitting into sections of length of 120 words, using them to create an expanded data set by preserving the associated labels. For inference, after fine-tuning, the expanded data set entries are rejoined along with their predictions. We can see here the distribution of original text lengths and the text length after applying the data transformation function. There are advantages of text splitting for multi-label classification, as an increased number of instances in the expanded dataset improves the statistical basis of our model and its bias. And this is a type of data oversampling, as an ensemble model is created per each instance, and output predictions are made by aggregating all predictions over each original instance, which improves prediction variance. Well, we have generated 10 base models, fine-tuned each on a newly resampled dataset using transfer learning from pre-trained transformer models as per Roberta, Albert, and ExcelNet. And for fine-tuning, we use the simple transformers library, which where we take advantage of the default model arguments available. And for fine-tuning, we use a loop where we firstly resample data from the training set, then we perform data transformation, obtaining the expanded train and test sets, on which we fine-tune from the pre-trained LM, we save the model state, and then we clear the model state and we reinitialize the model at the beginning of the next step in the loop. For inference, we aggregate the base models as the mean of their prediction arrays, thus generating the ensemble model prediction array. For optimization, we use microF1 with thresholding to find the best 3 models on the expanded dataset. And on the rejoined dataset, to find the optimal prediction threshold, we use sample average F1. Other means of regularization during fine-tuning, we apply label weights. This is just to compensate the label imbalance while training. We have generated homogeneous ensembles by aggregating ensemble predictions over the one and each pre-trained model. So we create a mean model by averaging prediction arrays of 10 base learners. The best 3 model is obtained by averaging predictions arrays from best 3 models, and then we compare this with the best model. And the heterogeneous ensembles are obtained by averaging prediction arrays from best 3 models from each language model. The results from our experiments are presented here for datasets A, B, and C for heterogeneous and homogeneous models. And we observed that there are some improvements between the homogeneous models and the heterogeneous ones, but these are very small, between 1 and 2%. For example, here in the rejoined dataset of heterogeneous models, we obtain a microFON of 0.82, comparing to a 0.81, for example, here in the rejoined data in dataset A. There is also an important increase of about 5 to 8% in scores between the expanded model and the rejoined model. For example, in dataset A, we can see the increase from 0.73 to 0.81 microFON between the expanded and rejoined data, and this occurs for all 3 datasets. Looking at baselines, we have chosen to use the lean SVC and multinomial naive Bayes from sklearn multilevel classification library. The lean baseline has high scores for dataset C, as one versus rest approach performs well on data with low imbalance ratio, but somewhat lower scores on datasets A and B due to difficulties of binary relevance type algorithms on data with high label imbalance. The multinomial naive Bayes cannot handle the data complexity and obtains much lower scores. As a result, we conclude that text length in each entry and the imbalance ratio play a significant role in the fine-tuning performance. Conclusions: we have performed multi-level classification on imbalanced datasets subsampled from legal test datasets provided in LexGlue. We designed a pseudo-stratified sampling method for imbalanced multi-level datasets, and we generated deep learning ensembles of Bayes learners built as fine-tuned transfer models. The main takeaway is that there is a score improvement between the expanded and the rejoined data sets in the range from 5 to 8%, which implies that text splitting improves classification outcomes at aggregation time. We obtain best scores between 0.78 and 0.82 microF1, which are quite good values for this type of problems. And last but not least, using the GPUs on Google Colab, the training times per model are between 2 and 15 minutes per epoch, and inference times between 1 and 3 minutes per model. When we use very small test sets, the inference times are very, very short, which is an advantage for online applications. The training times increase with the number of instances and base models, but for small data size, when we use small data sizes, this leads to acceptable times for generating and using ensembles of 10 models. Thank you for your attention.